Swayam Prabha. Digital India. Educated India.
Now, we are going to see the continuation of matrices. The matrices actually operator, and then based on the matrices, some of the elementary numbers we have to fix in terms of the vectors. Therefore, next we have to start with the vector space. Now, based on the definition, let us go to the deep of the vector space. I hope all of you know about that group theory. Group theory is nothing but what a non-void set G comma star is said to be a group if it satisfies the following conditions. One is closed, and number 2 is associative property, number 3 is existence of identity, and number 4 is inverse property. So, based on this we have to discuss the further analysis of vector space. So, first let us start with a non-void set V. Non-void set V in the sense that it is a non-empty. Non-empty means at least the set having one element is said to be non-empty. Now, we have to use the operation, binary operation. Binary mean you put a star. Star is a binary notation. It consists of what? Any two number you take it and then insert the operation is said to be binary. Bi mean two, nary mean operation. So, binary A star of B you have to use it. So, A star of B you have to use it. Here star can be represented as either plus or dot. But in vector space we have to use both at a time, plus as well as dot. So, that is most important for introducing the operation. So, the real valued mean all the numbers are you taken into account of real numbers, and a real number you have to take it, and you take a set V with the two operation. One is called it as a plus. In a Cartesian product, nu cross nu or V cross V, whatever may be the symbol, you take a Cartesian product from x axis and y axis, say like this, V to V, and then you have a point on the first quadrant. So, let it be A comma B using the operation, so that the resultant will be a point will come, that is a V. So, that is a mapping we have to introduce. And another one is parallelly you have to take into account of a dot is a product. So, R cross V maps to V. So, that is the meaning of parallelly you have to use the what? The operation mapping from domain to codomain, and then we have to describe what? The operation A star B, and A star B is as your assumption to use the operation, maybe it may be A plus B minus AB or A plus B, like that, whatever may be the definition you can impose it, so that the operation between the two things will be exist. Then check it out whether it is a vector space or not. So, taking into account of this, where let us continue with the definition of binary operation of A and B, where V comma plus is an abelian group, and also it satisfies the distributive property that for all lambda in R is a scalar, x comma y in vector, and lambda into x plus y equal to lambda x plus lambda y, and similarly for all lambda comma psi in R, then x in nu or v, and then lambda plus psi into x equal to lambda into x plus psi into x. So, this is called it as a distributive property of right as well as left. And then third one is associative based on the scalar for all lambda as comma psi in R and x in V, and lambda into psi into x equal to lambda psi into x. Then we have a neutral element with respect to the outer operation for all x in V, then 1 into x equal to x. So, this is the fundamental definition of vector space. Now, the elements x in V is called a vectors. Vectors mean having the orientation and direction, and then neutral element of neutral element of nu comma plus is a 0 vector, where 0 equal to 0 0 0 of transpose in the sense that n dimensional, and inner operation plus is called a vector addition. So, the elements lambda in R are called scalars, and the outer operation is a multiplication by a scalar. That is the meaning of the vector space. Now, we will go to discuss examples of the vector space. Let us have a look at some important examples. Let V in R power n mean the n tuple, where n belongs to n is a vector space with the operation defined as follows. Take two elements x and y, and x can be written as a n tuple, x1, x2 and so on xn, and y can be written as y1, y2 and so on yn. Then corresponding entry you have to add x1 plus y1 and x2 plus y2 and so on xn plus yn. Then the resultant is x1 plus y1 comma x2 plus y2 and so on xn plus yn for all x comma y in R. And if you use the multiplication by scalar, then you have to take lambda x, which is equal to lambda of x1, x2 and so on xn, which is equal to lambda x1 and so on lambda xn for all lambda in R and x in R power n. And V is equal to R power m cross n, mean m rows and n columns of the tuples, and then R is a real number, m comma n belongs to natural number, is a vector space with, you take a two number a and b, add them, a11 plus b11 and so on, a1n plus b1n and so on, amn plus bmn and so on, amn plus bmn is defined element wise for all a comma b in V. And we have a multiplication by scalar, lambda a equal to lambda a11 and so on lambda a1n, lambda amn and so on lambda amn as defined in the section of this area. And remember that R power m cross n is a equivalent to R power mn. And if you choose V equal to C, C mean complex, with the standard definition of addition of a complex number also it is applicable. Next remark, in the following we will denote a vector space V comma plus comma dot by V when plus comma dot are a standard vector addition and a scalar multiplication. Moreover, we will use the notation x in V for the vectors in V to simplify the notation so that it easily understand. Next note, the vector space R power n comma R power n cross 1 is n tuple with one column, R power 1 cross n is one tuple cross n tuple and then one rows of n elements, or only the different in the way of writing a vectors. We will make a distinction between the n tuple R and n cross 1 tuples of R, which allow us to write the n tuple as a column vector x equal to x1, x2 and so on xn. So, this simplifies the notation regarding the vector space operation. However, we do distinguish between r power n cross 1 and r power 1 cross n, the row vectors, to avoid the confusion with the matrix multiplication. The default, we write x denote the column vector and a row vector is denoted as x transpose. Therefore, it is represent a transpose of x. Next, we will go to the vector space, and vector subspace also we have to discuss. Next, we are going to discuss vector subspace. So, vector subspace means how we are defining the subset of one set to the another, how we are defining subgroup of a group like that. Same way, we take a vector space and you take a subset and follows with the definition is said to be vector subspace. So, let V equal to V comma plus comma dot be a vector space, and U is a subset of V which U not equal to 0, then U equal to U comma plus comma dot is called vector subspace of V or linear subspace of vector. If U is a vector space with a vector space operation plus and dot restricted to U cross U and R cross U, we write U is a subset of V to denote the subspace of U of V. So, that is the meaning of what? Subspace, vector subspace. So, what you can infer, you take a V and you take a subset U, and U is a subset of V and V is a vector space. U naturally inherits many properties directly from V because they hold for all x in V, and in particular for all x in U is subset of V. This includes the abelian group properties, the distributivity, the associativity and neutral elements. So, determine whether U comma plus comma dot is a subspace of V. We still do need to show, number 1, U is not equal to 0, in particular 0 belongs to U. Number 2, it is a closure of U with respect to the outer operation lambda in R, x in U, so lambda x in U. With respect to the inner operation for all x comma y in U, therefore x plus y belongs to U. Now, we are going to discuss one example. Take a look of the one example. For every vector space V, the trivial subspace are V itself and 0, that is a trivial case of the vector subspace. So, only element D in the figure 2.6, this is 2.6 is a subspace of R square, right. So, only element this with the usual inner outer operation, and in A and C the closure property is violated and B does not contain 0. So, this is the explanation given in a picturized form. So, the solution set of homogeneous system of linear equations Ax equal to 0 with n unknowns, where x varies from x1, x2 and so on xn in n tuple, and it means T is transposed in the representation of a Cartesian product is a subspace of R power n. So, the solution of the inhomogeneous system of linear equation, right hand side having the value Ax equal to B and B not equal to 0 is not a subspace of R power n, because we could not do that. So, the intersection of arbitrarily many subspaces is a subspace of itself. So, these are all the well known examples of a vector subspace. Now, we have a note, every subspace U is a subset of R power n comma plus comma dot is a solution space of homogeneous system of linear equation Ax equal to 0 for all x belongs to R power n. So, this is the well known example of vector subspace. Next, we are going to discuss the linear independence. Now, before going to discuss linear independence, we should know what is the meaning of linear combination. So, linear combination means consider a vector V and a finite number of vectors x1, x2 and so on xn belongs to V, then every V in V of the form some scalar times of the vector plus another scalar times of the vector and so on, another scalar times of vector, you have to do that. That is, V can be expressed lambda 1 into x1 plus lambda 2 into x2 and so on, lambda k into xk. Then we have what, summation I equal to 1 to k lambda I xi belongs to V. So, here all the lambdas belongs to R is a linear combination of the vectors x1, x2 and so on xk. So, this is the meaning of linear combination of vector in terms of the scalar. Therefore, any vectors can be written as some scalar times of the vector and another scalar times another vector and so on, and this have to remember, then only we think about that the each set as a linearly independent or dependent we can easily identify. Based on this definition, we have to go to the next definition is linearly independence. Let us consider a vector space V with k in n mean natural number and x1, x2 and so on xk are a vector. If there is a non-trivial linear combination such that, see earlierly we discussed this, suppose the right hand side equal to 0, then 0 equal to summation I equal to 1 to k lambda I into xi. Therefore, where lambda I not equal to 0 mean the set of all vectors x1, x2 and so on xk are linearly dependent and the only trivial solution exists. If all scalar equal to 0, then it is said to be what, linearly independent. So, this way we can identify whether the vector is a linearly independence or dependence. So, dependence mean any one of the scalar not equal to 0, then it is dependent. If all scalar equal to 0, then it is said to be linearly independent. Next example, linearly dependent vectors. The geographic example may help to clarify the concept of linear independence. A person in Nairobi, that is in the Kenya, describing where Kigali, Rwanda is might say you can get to Kigali by first going 506 kilometer northwest to Kampala, Uganda and then 374 kilometers southwest. Like that you have to take it into account of the mapping and we are going to that. So, this is sufficient information that the ideas of describing the Kigali, because this geographic example may help to clarify the concept of linear independence. So, the person in Nairobi, Kenya describing where the Kigali is might say you can get to Kigali by first going to 506 kilometer northwest to Kampala, that is Uganda, and then in 374 kilometers southwest. So, this describes the location of Kigali because the geographic coordinated system may be considered a two-dimensional vector space ignoring altitude and the earth's curved surface. So, the person may add it is about 751 kilometer west of here. Although this last statement is true, it is not necessary to find Kigali given the previous information, and follow with the figure 2.7 for an illustration. In this example, the 506 kilometer northwest vector blue and the 374 kilometer south vector purple are linearly independent. This means the southwest vector cannot be described in terms of the northwest vector and vice versa. However, the third 751 kilometer west vector black is a linear combination of other two vectors and it makes the set of vectors linearly dependent. So, equivalently given 751 kilometer west and 374 kilometer southwest can be linearly combined to obtain 506 kilometer northwest. So, this is the description of the ideas based on the linear independent and dependent. Now, you can see the Kigali and Nairobi and in between the Kampala. go to the direct without touching the Kambla, we can directly go to the Nairobi, and then we can reach from southwest to the northwest and 374 kilometer and 506 kilometer from Kambla to Nairobi. Whereas if you go directly from Kigali to Nairobi, then 751 kilometer west. Note that this geography is with a crude approximation to cardinal direction of linearly dependent vectors in a two-dimensional space. Now note that the following properties are useful to find out whether the vectors are linearly independent. Now k vectors are either linearly dependent or independent. There is no third option. If at least one of the vectors x1, x2, xk is 0, then they are linearly dependent. The same holds if two vectors are identical. The vectors x1, x2 and so on xk and xi not equal to 0, where I varies from 1 to k, where k is greater than or equal to 2, are linearly dependent if and only if at least one of them is a linear combination of the other. In particular, if one vector is a multiple of another vector, that is xi equal to lambda xj, where lambda in R, then the set x1, x2 and so on xk, xi not equal to 0, where I varies from 1 to k is a linearly dependent. A practical way of checking whether the vectors x1, x2 and so on xk in V are linearly independent is to use the Gaussian elimination. Write all vector as a columns of the matrix A and perform Gaussian elimination until the matrix is in the row echelon form. The reduced row echelon form is unnecessary here. The pivot column indicates the vectors which are linearly independent of the vectors on the left. Note that there is an ordering of vectors when the matrix is built. So, the non-profit column can be expressed as a linear combination of the pivot column on the left. For instance, the row echelon form 13002 tells us that the first and third columns are pivot columns. The second column is a non-pivot column because it is a 3 times of the first column. All the column vectors are linearly independent if and only if all the columns of the are pivot columns. If there is at least one pivot column, the columns and therefore the corresponding vectors are linearly dependent. So, these things you have to remember so that you can understand the with application linearly independent and dependent. Next example, consider a 4 tuple with x1 equal to 1, 2, minus 3, 4, x2 equal to 1, 1, 0, 2, x3 equal to minus 1, minus 2, 1, 1 like that. Now check whether they are linearly dependent. So, we follow the general approach to and solve lambda 1 x1 plus lambda 2 x2 plus lambda 3 x3 equal to lambda 1 into this vector, lambda 2 into this vector, lambda 3 into this vector. Now, we can write for lambda 1, lambda 2, lambda 3 the vectors I equal to 1, 2, 3 as the columns of the matrix and apply elementary rows operation until we identify the pivot column, right, 1, 2, minus 3, 4, 1, 1, 0, 2, minus 1, 2, 1, 1. After row reduce and column reduce, simplify, we have 1, 1, minus 1, 0, 1, 0, 0, 0, 1, 0, 0, 1. Therefore, every column of the matrix is a pivot column, right. Therefore, there is a no non-trivial solution. So, we require lambda 1 equal to 0, lambda 2 equal to 0, lambda 3 equal to 0 to solve the equations. Hence, these vectors are linearly independent. Or you take a square matrix, subsquare matrix, do the process of what row reduce column, check it out. If determinant is check it out. If determinant equal to 0, then it is independent. Determinant not equal to 0, then it is linearly independent. So, determinant equal to 0 dependent, determinant not equal to 0 is linearly independent. Now, note that we have a note, consider a vector space P with k linearly independent vectors and b1, b2 and so on bk are m linear combination, then x1 equal to summation I equal to 1 to k lambda I 1 bi and so on, xm equal to summation I equal to 1 to k lambda I m bi. So, by definition B equal to b1, b2 and so on bk as a matrix whose columns are linearly independent vectors b1, b2 and so on bk, we can write j equal to b into lambda j, where lambda j equal to lambda 1 j and so on lambda k j, where j equal to 1 2 and so on m is a more compact form. So, we want to test whether x1, x2 and so on xm are linearly independent. For this purpose, we follow the general approach of testing when summation j equal to 1 to m, psi j xj equal to 0, with the previous equation we obtain summation j equal to 1 to m, psi j xj equal to summation j equal to 1 to m, psi j into where xj equal to b into lambda j, substitute it. So, b is a constant, take it outside. So, b into summation j equal to 1 to m psi j into lambda j. This means that x1, x2 and so on xm are linearly independent if and only if the columns of the vectors scalar lambda 1 lambda m are linearly independent. So, shall we go to the one more example? Before that, one note, in a vector space V, m is a linear combination of k vectors x1, x2 and so on xk are linearly dependent if m is greater than k. For example, consider a set of linear independent vectors b1, b2, b3, b4 and it belongs to n tuple, and x1 equal to b1 minus 2b2 plus b3 minus b4, and x2 equal to minus 4b1 minus 2b2 and plus 4b3 b4, and then x3 equal to 2b1 3b2 minus b3 plus minus 3b4, x4 equal to 17b1 minus 10b2 plus 11b3 plus b4, or the vectors x1, x2 and so on x4 belongs to n tuple are linearly independent. Now, to answer to this question, we investigate where the column vectors 1, first column 1, minus 2, 1, minus 1, that is x1 coefficient you take it and write in the column. Similarly, x2 take it coefficient, you write the column way minus 4, minus 2, 0, 4, and x3 is 2, 3, minus 1, minus 3, and x4 is 17, minus 10, 11 and 1. So, you take into account of this, convert into matrix, check it out by row reduce, column reduce, and then or determinant of the given matrix you take it. If determinant is equal to 0, then it is a dependent. If determinant not equal to 0, then it is linearly independent. Now, or linearly independent, the reduced row echelon form of the corresponding linear equations of the system of coefficient equation A is equal to like that matrix form represent, and then row reduced matrix you have to do that, you can get the simplified form like this. Now, we see that the corresponding linear equation system is non-trivial solvable. The last column is not a pivot column, therefore, x4 equal to what? Minus 7 x1 minus 15 x2 minus 18 x3. Therefore, this values x1, x2, x4 are linearly dependent. Therefore, x4 can be expressed as a linear combination of x1, x2, x3. Now, we are going to discuss basis and rank. So, before going to basis and rank, let us start with generating set and basis. The definition of a generating set is nothing but consider a vector v, v comma plus comma dot, the set of vectors a equal to x1, x2 and so on xk in v. Now, if every vector v in capital V can be expressed as linear combination of x1, x2, x3 and so on xk, where A is called a generating set of vector V. So, that is the meaning of generating set. Mean the linear combination of one vector to the another is said to be generating. Now, the set of all linear combination of the vectors A is called span of A. It means a span of vector V can be written as one vector in terms of the another vector is said to be what? Span of vector. So, x1 can be expressed in terms of x2, x3, then x1 span with x2 and x3 like that. So, then V can be written as span of x1, x2 and so on xk. So, this is the meaning of generating set and spanning set. Next, we are going to discuss the definition of basis. Consider vector space V, V comma plus comma dot, and A is subset of V. So, a generating set A of V is called a minimal if there exists no smaller set A which is subset of not subset contained A contained in V. So, subset not equal to in the sense that this is contained in V, that is superset is also included, then we have to do the meaning of A tilde subset of A and superset also given, then it is said to be what both set as well as superset also included, then that will be span. So, from this what we can infer, every linear independent is a generating set of V is a minimal and is called a basis of V. So, let V equal to V comma plus comma dot be a vector space and B is a subset of V and B not equal to 0, then the following statements are equivalent. Number 1, B is a basis of V and B is a minimal generating set and B is a maximal linear independent set of vectors in V, and adding any other vectors to this set will make it is a linearly dependent. That is a condition of what the vector should be what followed with the bases generating and a linear independent dependent, and every vector x in V is a linear combination of the vectors from B, and every linear combination is unique with x equal to summation I equal to 1 to k lambda I bi, which is equal to summation I equal to 1 to k psi I bi, and lambda I and psi I belongs to R and bi in B, then it follows that lambda I equal to psi I where I equal to 1 to k. So, this is the meaning of the vectors can be written as linear combination of the other. For example, in R cube 3 tuple, the canonical standard basis is B equal to 1 0 0 0 1 0 0 0 1. Now, the different bases in R cube are B1 equal to this and B2 equal to this set of vectors. Now, so these are all the different bases and then we can check it out whether linearly independent dependent, right. Now, you have to do with the testing of what determinant or ordinary method of row reduce column reduce, so that you can get the what solution to the problem. Now, the set A equal to 1 2 3 4 2 minus 1 0 2 1 1 0 4 0 minus 4 is a linearly independent, but not a generating set. For instance, the vector 1 0 0 transpose cannot obtain the linear combination of the element in A. Note, every vector space V possesses a basis B. The preceding example show that there can be many bases for the vector space V, that is, there is no unique basis. However, all bases possesses the same number of elements, the basis vectors. So, that things you have to remember. Next note, the dimension of a vector space is not necessarily the number of element in a vector. For instance, the vector space V equal to span 0, 1 is a one dimensional, although the basis vector possesses 2 elements. So, that thing you have to remember for not necessarily number of elements in a vector. Next note, the basis of the subspace U equal to span of what the vectors x1, x2 and so on xm. That is, you have to take a set of vectors which is a spanning of one element to the another, means the linear combination of one to another, that is also a basis of the subspace in Rn. Rn mean n tuple can be found by executing the following steps. Number 1, write the spanning vectors as a column of a vector A, determine the row echelon form of A, and third one, the spanning vectors associated with the pivot columns or the basis of U. So, these steps you have to follow that if the vector having the basis of the subspaces. Now, let us go with one example. So, determining a basis, Now, for a vector subspace U in R power 5 spanned by the vectors, let it be x1 equal to 1, 2, minus 1, minus 1, minus 1, x2 equal to 2, minus 1, 1, 2, minus 2, and x3 equal to 3, minus 4, 3, 5, minus 3, and x4 equal to minus 1, 8, minus 5, minus 6, 1 in R power 5, mean 5 tuple. Totally each set having a 5 elements. Now, we are interested in finding out which vector x1, x2 and so on x4 are a basis for U. For this, we need to check whether x1, x2 and so on x4 are linearly independent. Therefore, we need to solve summation I equal to 1 to 4 lambda I xi equal to 0, which leads to homogeneous system of equation with the matrix, that is a set of vectors x1, x2 and so on x3, x4 is equal to matrices having what? That is 5 rows and 4 column, 1, 2, 3, minus 1, 2, minus 1, 8, and then minus 1, 1, 3, minus 5, minus 1, 2, 5, minus 6, and minus 1, minus 2, minus 3, 1. So, keep it in mind of this set of vectors. Now, we have to use the row reduced matrices, that is make the leading element of all the, say this is main diagonal, you take it, right, and then leading element you have to convert into 1, and then below the diagonal element or below the numbers make it as 0, so that the problem will reduces to simplest form. Now, you have to consider the matrices like this, and then row reduce, you do that R1, R2, this is R1, R2, R3, R4 and R5, and then subtract from one another, or you have to manipulate in this way, then you have to get 0, you have to get 0 here, 0 here, 0 here, and then make rest of the elements as it is, as well as keep it as the rest of them bring it to 1, and now you take into account of this, right. Now, you take the square matrix, find the determinant. Now, you take this determinant here, maximum is what 3 cross 3 is here, or what you have 3 cross 3 matrix like this, and find the determinant 2, 3, minus 1, 1, 2, minus 2, 0, 0, 1, and expand the determinant. So, we have what 2 into 2, 0, and then minus 3 into what 1, and then minus 1 into 0. Now, what happened? 4 minus 3 equal to 1, not equal to 0. Then we can check it out and what type of the matrix it is. If determinant subsquare determinant is not, if original determinant you take it, that becomes 0, and subsquare you take it, then it is linearly dependent will come. Now, since the pivot columns indicate which set of vector is linearly independent, we see from the row echelon form that x1, x2, x3, x4, x1, x2, x4 are linearly dependent, because the system of linear equation lambda 1 x1 plus lambda 2 x2 plus lambda 4 x4 equal to 0 can only be solved when all the lambdas equal to 0. Therefore, x1, x2, x4 is a basis of U. Now, we have a rank. So, the number of linearly independent column of a vector of the matrix A belongs to R power m cross n equals the number of linearly independent rows and is called the rank of A. So, you have to consider what matrices previously, previous you take it. So, this one you have to take it. Based on this, we can check it out the rank. If original matrix determinant find out if it is equal to 0, then that is not a rank. So, first you have to check it the order of the matrix. So, order of the matrix should be n cross n, and then if rank of A equal to determinant not equal to 0 is a rank n. And then if it is equal to 0, then go to the subsquare matrix. Any subsquare matrix of the matrix you have to take it not equal to 0, then that is a rank. So, from this what we can infer, the rank of the matrix has some important properties. So, rank of A equal to rank of A transpose, that is column rank equals the row rank. The column of A belongs to R power m cross n span, a subspace U belongs to a subset of R power m, and dimension of U equal to rank of A. Later we will call this subspace the image of R range. So, a basis of U can be found by applying Gaussian elimination to A to identify the pivot column. Next, the row of A belongs to R power m cross n, span a subspace W is a subset of R power n with dimension of W equal to rank of A, and a basis W can be found by applying Gaussian elimination to A transpose. For all A in R power n cross n, it holds that A is regular and invertible if and only if rank of A equal to n. So, this is the things you have to remember if rank is determined with the help of the entry given in the matrix. For all A belongs to R power m cross n and all B in R power m, it holds that the linear equation system Ax equal to B can be solved if and only if rank of A equal to rank of AB augmented matrix, where A divides B denotes augmented system. For A in R power m cross n, the subspace of the solution for Ax equal to 0 possesses a dimension of n minus rank of A. Later we will call this subspace the kernel or the null space. So, a matrix A in R power m cross n has a full rank if its rank equals the largest possible rank for the matrix of the same dimension. This means that the rank of full matrix is the lesser of the number of rows and columns, that is rank of A equal to minimum of m comma n. So, the matrix is said to be rank deficient if it does not have a full rank. Next example, rank A equal to 1 0 1 0 1 1 0 0 0 as a two linearly independent rows column. So, that now you check it out, determinant of A. So, determinant of A is equal to 0 and you take a subsquare matrix 1 0 0 1 and we have a 1 which is not equal to 0, therefore, the rank is 2. So, this way we have to check it out what type of the rank it has. Now, you take another example 1 2 1 minus 3 minus 2 minus 3 1 3 5 0. Now, you check it out the determinant of 1 2 1 minus 2 minus 3 1 3 5 0. Now, expand it 1 into 0 minus 5 minus 2 into 0 minus 3 and 1 into minus 10 plus 9. Now, we have minus 5 and plus 6 and then we have a minus 1, 0, therefore rank of A not equal to 3. Then you take a subsquare matrix 1, 2, minus 2, minus 3 and find the determinant, then it is not equal to 0, therefore rank of A equal to 2. So, this way we can find the rank. Thank you.